Hi, my name is Pranav Varshney, and this is my EECS 281 IA application. Let's start off with this handwritten problem, very similar to what you'd be seeing in lab. Given n ropes, we want to find the minimum possible cost of connecting the ropes together, where the cost of connecting two ropes is the sum of their length. So what I'm already thinking is we want to have some sort of greedy algorithm where we take the two smallest ropes together, connect them, and have that be the running cost of our total algorithm. So let's just look at the example really quickly. We have four ropes of length 10, 5, 8, and 11. Now, as we can see with the step one, two, and three, that idea of a greedy approach where we take the smallest ropes, connect them together is pretty correct, where we can see 5 and 8, we connect them together, 13. The next two smallest, 10 and 11, connect them, that's 21. The next two smallest is 13 and 21. What we want to do is we want to keep simulating this algorithm until we hit the PQ's size or like the size of the container to equal 1. I kind of spoiled a little bit, but the data structure that we would want to use in this case is a priority queue. Now, some of this code is like pretty useless. It's just filtering in this test.txt file to set the problem up. But we want to use a priority queue container. What a priority queue is it sorts or it orders the elements in the container based off of the priority that we give it. Now, in this case, the priority that we want is for it to be a min PQ, such that the minimum elements are higher in the priority queue. You can implement your own comparator to have your own sorting algorithm or your own sorting system. But in this case, we just want to use what C++ has to offer. So let's just quickly implement that right here. This is implementing a priority queue. That's a min PQ. And also what we want to do is we want to have this priority queue initialized to all of the elements in the ropes vector. And what we can do is we can just have a iterator, like the arguments of an iterator to the beginning and the end of the ropes container right here. So right now the PQ is initialized to all the elements in ropes, but in a min order. So it'd be 5, 8, 10, 11. We also want to have a running cost sum, running cost variable that keeps all the costs together. As we kind of stated earlier, we want to keep doing this algorithm until the rope is one big rope. So while the priority queue's size is not equal to 1, we want to keep continuing to do this problem. What the problem is we want to take the first and the second element and we want to find the sum between them, add that to our running cost, and also add that back to the priority queue because we can use that connected rope in the future. So let's just implement that really quickly here in first and in second. Now we have a new rope that's of size or length equal to first and second. That's what we're adding to our sum or our cost. And that's also what we're going to be pushing back into the priority queue. So ideally, this should return to us, if we return cost, our output should give us the total cost correctly of 68. So let's just quickly run that in our terminal. As you can see, the total cost is equal to 68. So the algorithm is working correctly and as intended. Now we can do some runtime analysis of this data structure and how exactly the algorithm works. The priority queue's underlining data structure is a binary search tree. If you haven't learned about that, I'd like recommend you to look it up. It's a really cool data structure. And what it allows us to do is have an insertion of log n. As we traverse down the binary tree, it'll take us log n time. And then we'd insert a new node with the value that we currently have there. It's a really cool, really nifty algorithm or really nifty data structure that we can use for log n insertion and O of 1 deletion because we can just pop that node off, pop that pointer off. So that's the runtime analysis of the actual data structure. And that kind of correlates or extends towards our algorithm right here, where we have n log n insertion time, and we do that right for all the n elements in ropes log n times. So that's n log n insertion. And then O of 1 deletion, which is pretty trivial, it doesn't really matter. And we keep doing that for pq.size is until it's equal to 1. So that's basically the algorithm. this into main function is basically parsing in the test.txt for us to be able to use. That's the algorithm, and priority queues and greedy approach summarized pretty quickly. Thank you.